Resolution in thin films. Prob number 2. We have two stars 20 light years away. That's a long way. They're barely resolvable by a 12-inch mirror telescope. Barely resolvable means that it satisfies the Rayleigh criterion. So the question is, how far apart are the stars? And here's the wavelength and distance light, the speed of light. And so let's take care of that. All of that. So problem number 2, we have the situation is we have a very long distance away between the stars. D is equal to 20 light years, LY, 20 light years. Now, I hope you realize that the angle between the stars, here's a star, say S1 and S2. This is going to be a very skinny triangle, because the angles we deal with telescopes and resolution are very small angles, but we are looking for theta. So that's at least part of what we're looking for. To solve this problem, because this is a very skinny triangle, you can consider the adjacent side and the hypotenuse the same length, and actually both 90 degrees, essentially. Therefore, we can say that the tangent of theta is equal to, let's go ahead and call this y, opposite over adjacent, y over big D. And so, what we want to discover is the separation distance. Y is equal to d tangent of theta. This is the formula that we want to plug stuff into. But we don't know d. Oh yeah, we do, 20 light years. And we don't know the angle. So let us discover those. D, let's do that first, because that's pretty straightforward. We have 20 light years, and we have, that means the distance light travels in 20 years. Well, it's 3 times 10 to the 8th meters per second, and the conversion from seconds to minutes and hours is multiplying it by 3,600 seconds per hour. So that makes the seconds go away. And then 24 hours per day makes the hours go away. And 365, good enough, days per year makes the days go away. And let's see, so we have all that. And that should give us 1.89 times 10 to the 17th meters. So that's a lot of meters, a whole lot of meters. So now we have d in this equation, and now we just need theta. What is theta? Well, since they're just resolvable, it means the Rayleigh criterion is satisfied, which means that we have big D, I'll say, sine of theta. No. Not use big D. Let me start this over. D sine of theta is equal to 1.22 lambda for a spherical aperture. Okay, and this is the D. It's the diameter of the lens, or mirror in this case. So we're looking for the angle. Well, the sine of theta then is equal to 1.22 lambda over D, or theta is equal to the inverse sine of 1.22. Now, lambda is 550 nanometers, so 550 times 10 to the negative 9. Those standard units here with meters. Diameter. Okay, the diameter. It's 12 inches 12 inches. And I give you that, there's 39.37 inches per meter. So we're going to divide that by 39.37 inches per meter to give us meters here. Okay, this is a little bit cumbersome, I realize, in my little equation here. There. All that, which should be equal to inverse sine of 2.2 times 10 to the negative 6, which is equal to 1.26 times 10 to the minus 4 degrees. Okay, so there's the very tiny angle that we solved out of this using the Rayleigh criterion. That, of course, goes there. Okay, and so y is equal to then d 1.89 times 10 to the 17 tangent of the angle 1.26 times 10 to the negative 4. And that should be equal to 4.16 times 10 to the 11 meters. And there is our separation distance. All right, so that's not that small of a distance. This is 10 to the 11th is 100 billion. So 400 billion meters, which is, again, not too small. But compared to 20 light years, yeah, it's pretty small. Because a light year is about 6 trillion, and there's 20 of those. Okay, so that takes care of that, what seemed like a hard problem. Tamed it a little bit.